All right, let's go ahead and get started here. All right, we've got a solid number of attendees here. Thank you very much for joining. This is webinar number 2 in the series of 10. This is our 2021 Apex webinar series. Today we'll be talking about mid-surfacing and shell meshing of complex geometries. But before we get into that topic, I just wanted to give everybody a reminder of what this webinar series is actually about. You can see here that we are on number 2. We are in March, we're talking about best practices, mid-surfacing, and shell meshing, but this is really the best practices series. So what we did is we contacted a number of our strategic customers and partners around the world, and we said, what do you guys want to know about when it comes to Apex? And these 3 best practices webinars came up: geometry cleanup, mid-surfacing, and shell meshing, as well as dynamics, frequency response dynamics analysis. So those are the 3 that we'll be talking about. The next series of webinars that you guys asked for was an interoperability series. As you know, Apex is more than just a preprocessor for MSC Nastran. It is a platform for a number of different tools, and 3 tools specifically that you, our customers, asked for and continue to ask for is: how do you use Apex with Patran? How do you use Apex with Atoms, including their preprocessor Atoms View? And also our nonlinear solutions. Now, we're not actually calling out a product because actually there's 2 in here, both Nastran Sol 400 as well as Mark for advanced nonlinear analysis. So we'll be talking about all of that later on this year. All right. Now, a few of you also said, well, what about my specific industry? And we said, okay, well, let's take probably some of the most popular ones and the most asked about ones that are currently using MSC Apex. And the 3 top ones are space applications, aircraft conceptual modeling, like internal loads and conceptual aircraft sizing, and automotive applications. So things like mid-surfacing and shell meshing for, say, like a LS Dyna crash model, or if you have an injection molded plastic part or something like that that you wanted in the automotive industry. So those are the 3 that made it there. Now, the last one that we wanted to talk about, kind of the one that just stuck out like a sore thumb, doesn't really have a whole bunch of other series type of webinars, but is no less important. In fact, it's asked about at least probably once a week, if not multiple times per week, is the Python API built in within MSC Apex. And so the very next one, we'll have one of our guest speakers talk about the Python scripting and utilities commands, both from a pre-processing as well as interoperability and maybe even some post-processing scripting as well, if you guys are lucky, okay? So stay tuned for that. We've got some exciting ones. Now, let's talk about what the 2021 releases look like, okay? So we've switched from 2 releases per year to 4 releases per year, okay? So every 3 months, you've got a brand new release of MSC Apex. Some of you have even been involved in our beta testing program. We extend invites to a select number of longtime users of MSC Apex to become our trusted advisors for the future of the product. So you'll be getting emails about that 4 times per year. Okay, now previously when it was only twice a year, we had a live webinar, much like this one, for each new release. Now, since then, MSC has acquired a number of different products, as well as switching to 4 releases per year. We just figured it was just too much to have a live webinar for the beta and a live webinar for the GA release 4 times a year. And most of you guys, Apex is not the only tool that you use, so you're attending live webinars for Nastran and Atoms and Mark and other tools as well. We just thought it was just too much. So we decided, instead of requiring you to attend a live webinar, instead we are doing 2 things for Apex and for other products in our portfolio as well. For the products that have a lot of features and functions and a lot of development going on, we're going to do 2 videos. For the lighter releases, we'll only do 1 video. But for Apex specifically, because there's so much hot and heavy development happening right now, we're gonna, for each release, we'll have 2 videos come out after the release comes out. We'll have a highlight reel, which for those of you that have a very tight schedule, just watch that one and you'll see a very quick 5-minute overview. And then video number 2, we'll have a technical deep dive. Now, this technical deep dive is sometimes 30, sometimes 45, sometimes an hour long. But this is basically replacing that what's new webinar that you guys are used to, okay? All right, so I am one of the product marketing managers here at MSC Software. I specifically focus on the GUIs for the structural analysis products. So Apex, Patran, CA Fatigue, as well as our platform Sim Manager for your PLM technologies. So I am the host for today. So just a quick reminder, we've got a very lively Q&A going on. You can send a question privately or you can send a question publicly. Feel free to send those at any point in time during the webinar. The quick questions, I might just fire back a quick response, or if you have a question that you specifically want to ask Steph, or you want me to ask Steph live, we'll do a Q&A session towards the end, and I'll gather all those up towards the end, and I'll ask Steph. Okay. Our presenter today is Dr. Steph Evans, who is one of MSC Software's esteemed international partners located in the UK. Most of you know him through his company, Evotech CAE Limited, or maybe even you know him from one of his amazing LinkedIn posts, which he's quite good at. Steph has actually spent the last 5 years running his company, Evotech, which, if I can say, offers an amazing set of training classes in MSC Apex. So if you haven't seen that, check that out. But before that, he actually spent 20 years in the aircraft industry. So he spent 20 years in the Airbus and the BAE Systems supply chain, doing exactly what we're talking about today, which is FEA development, analysis, and verification. Okay. So for that, I will go on mute and I will pass it over to Dr. Evans. Yeah.
Okay. Thank you, James. You can hear me okay?
Loud and clear. Right on.
Perfect. Okay, good morning, good afternoon, good evening, everybody. Thank you, James, for the introduction. My name's Steph Evans. I'm speaking today from the UK. We've got a beautiful spring day. The winter is finally over, I think, so everybody's smiling here. Okay, so I'm going to run through a number of aspects of the webinar today, focus on mid-surfacing and shell meshing. I'm just going to give you a quick overview, and then we're going to run into a series of how-to videos outlining some of the techniques that we'll talk about. Okay, so we're focused on a typical aerospace component. Many of you who've worked in the aerospace industry will be familiar with this type of structure, maybe a rib or a bulkhead, thin wall machining, sometimes known as a shear panel. Lots of different changes in thickness, lots of features, fillets, holes, steps, lots of entities to consider from an FEA model build analysis and verification perspective. Okay, so I'm going to run through 2 workflows. So the first workflow is going to be focused on what we call CAD to results. We used to talk about CAD to mesh, but Apex offers much more than that now. So we're, the full cycle, or product development cycle, if you like, for an FEA model, from source CAD, geometry preparation, mesh definition, and then finally attribution and verification through to a fully running model, whether the analysis is performed in Apex or externally using one of the tools that James mentioned. Okay, we're going to look at a second workflow as well, and some of the tools that you may or may not be aware of in Apex, looking at a legacy FEA model and what we call orphan model manipulation. So this is the situation where you've got maybe a legacy Nastran or legacy FEA bulk data file, and you can bring that into the Apex environment and manipulate it with no geometry in there whatsoever. Okay, so just a couple of approaches that we're going to work through today. Okay, so let's get started. The first one, workflow 1, CAD to results geometry preparation. So I've listed out a number of tips here. This is a best practice webinar, so we want to try and focus the mind on some of the things that will make your user experience as efficient as possible. So just listen these out, keep things simple. So important geometry, good practice to clean geometry before you start, to get rid of any errors or bugs in the geometry, and we've got simple tools in Apex to do that. Don't defeature when you don't have to. So taking this shear panel as an example, we've got lots of fillets and details in there. We're ultimately going to be generating a mid-surfaced, mid-surface surface, as it were. So there's little point in spending a long time defeaturing solids if the target model output is surfaces, okay? And then during the manipulation, it's probably good practice to delete unnecessary vertices and edges. So to try and simplify the geometry as much as possible to get us back to our bare bone surface for mesh development, okay? Second tip, automate when you can, okay? So there's many different techniques in Apex, just focusing on one here. So when we do the mid-surfacing, there are lots of surfaces that get stitched together. We've got tools like vertex edge drag. These are generally manual tools. So if possible, use automation where you can. And I'm talking automation within the Apex user interface. I'm not really talking specifically about the Python API here, but obviously there are opportunities for that kind of automation, and we'll probably cover that on the next webinar, as James mentioned. So yeah, extend stitch where possible. Use the appropriate auto mid-surfacing tool to suit your geometry complexity. So again, we'll see this in the example, but there are some simple tools for working with simple geometry, and then some more involved tools for looking at complex geometries where we've got lots of T sections, lots of joined and featured regions within the solid and then surface geometry. Okay. Tip 3, be clever with the display options. So Apex has really got some sort of state-of-the-art visualization tools. So you can use things like auto color to color individual entities in an automated sense before stitching, so you can see what's tied together, what isn't. We've got things like transparency mode, so you can overlay a transparent 3D solid over the mid-surface, and then you can sort of look at T-junctions, cruciforms, and that type of thing to see how the idealized surface relates to the master solid geometry. Okay, so we're now going to run through a quick example looking at these geometry preparation exercises, or steps, as it were. So this is a recording I made a couple of days ago, but it's actually recorded in real time. So everything you see is real. So there's been no edits or anything in there. So just brought in this shear panel from a Parasolid geometry file, CAD exports. You can see the features that we've got. So we've got lots of fasteners around the edges. We've got fillets, we've got steps, we've got variable shell thickness, or variable wall thickness, I should say. So perhaps not the most complex model in the world, but certainly useful for illustrating the type of thing that we're going to be looking at here. So in the model browser tree, you'll see that we've got a single solid entity. So the first one we're going to do, again, keeping things simple, is to clean the geometry. So we just go into the geometry cleanup tools, taking the default options, just hitting the solid, and then letting that run through, and there's a message in the bottom left-hand corner that the geometry has been cleaned. Okay, so we've got a really good starting point to work with. Okay, so now we're looking at mid-surfacing, and again, remembering we haven't done any defeaturing yet. Because we've got lots of surfaces, we're going to use the incremental mid-surface tool here. So what this does is we select the solid body, and then Apex works its way through and looks for paired surfaces to perform the mid-surfacing on. Okay, so we'll get this color code of surfaces. So the large web surface in the middle, the shear web, is colored in a yellowy color, along with the top flange. And then you can see for all the stiffeners in between, it's colored them uniquely based on what it deems to be a consistent pair of surfaces. So we can edit these. We can effectively make them all match up. So you can see for the horizontal and vertical stiffeners, we're just selecting discrete colors and then bringing them into one set. So again, color coded, so we can see really nicely the user feedback. And then we'll simply, once we're happy with those pairs, we'll simply select all the paired definitions, middle mouse button to apply, and then we've got all the surfaces extracted. Okay, so if you look in the model browser on the left hand side, you can see now we've got the original solid, and we've got many surfaces which have been brought out from the mid-surfacing operation. Okay, so again, a nice use of automation to try and speed up the process. If we try and again simplify things, we can use the auto color options in the model browser. So auto color each discrete entity. So we can see here we've got many surfaces which are not connected together. We could use the vertex edge drag, but we're going to try and automate as much as possible. So we're using the extend surface method, again with the default options, and this is going to snap edges together based on a predetermined tolerance. And then in the model browser, we've got a single surface entity, what we call a general body. So this is a body with T sections in it. Okay, so we can see with the display options, we've got the green shared, red free, and then yellow T section edges. And we can now start to use some of the vertex edge drag techniques just to tidy up the resultant geometry. So the incremental mid surface has done a really good job with the bulk of the model, but we've just got to tidy up some local areas. And again, using the edge display or the colors, we can see what's connected. Okay, so we can see in this region here, we've tied things together, but we've got some green edges which are sort of spurious edges that have been developed from the mid-surfacing. So we're just going to change the selection filter to edge and then select those and then delete them. If we can't delete an edge, then we might need to use again the vertex drag tool. So we'll put the vertices into view, and then we can just simply drag them across. So that this particular face would have had a subtle kink in it, but we've just flattened it out by moving those edges across. Okay, pretty straightforward, and again, really good user feedback in terms of what we're doing. So again, we've got all those teed edges where we need them. The geometry is pretty good to go. If we look at the model in plan view, we can see a typical cruciform where 4 surfaces have come together at a right angle. Okay, but there's one area where we don't have that cruciform geometry, so we can manipulate this if necessary. Probably not the best practice to have these offset stiffeners in this type of model, but it looks like the underlying CAD has got that. We could go with the model as it currently is, or we could tidy things up. We're going to move the profile to give us a cruciform geometry so that all 4 surfaces meet at a single edge. Okay, so just hide the solid geometry from view, and then we're going to use what we call a filler surface. So we pick an edge and then pick the next edge, and it fills in the surface between those 2 edges. Okay, you can see how those entities or those edges have snapped into the underlying geometry. Okay, so just for construction purposes, we're just going to extend this surface out of the way, and then we're going to split the surface using the edges of the original stiffener definition. Okay, so pick the surface, pick an edge. We can right click and select contiguous edges, and that will give us all the edges in the single run, and then we can see how the split's been made, and then we can change the selection filters and delete the original surface, or the stiffener surface that we no longer needed. Okay, we can see here that the split hasn't quite made it across, so we simply drag the vertex across, and we've now got a face which you can delete. Okay, so we've just tidied up that surface. So we're not sort of beholden to the underlying geometry, we're just using it as a starting point and then manipulating the mid surface as necessary. Again, so switching to the edge selection filter, picking the edges we want to delete, and they're gone from the model. Okay, again, really good feedback, really straightforward, nice way of working with the geometry. Okay, so we're just going to now look at an overlay. So we talked about some of the display options. So putting the solid back into view, and then we can select from the model browser that we want transparency. We're setting it to 80% transparent, and then we can look at the overlay between the mid-surface and the solid. Okay. Change the color just to make it a bit more obvious. There we are. Okay. So once we've got the shell properties defined, as a later step, we can compare those with the underlying surfaces as well. So we've probably built this full mid-surface definition in a matter of minutes. So really nice way of approaching this within Apex. Okay, just changing the color back. Sometimes it's nice to work with a gray background so you can see the edges. There are some features. So this ring step thickness, if you like, which have not been captured in the mid-surfacing. So we're just going to make some of those edits now. So pick the face, highlight the solid geometry, pick the edge, and then make the cut. It projects the edge onto the surface and then splits it. So you can see by virtue of the green line on the grey surface, we've got that in there. Okay, another step change here. So again, hiding the solid, picking the mid-surface, middle mouse button to accept, pick the edge. We're going to use the right button to select contiguous edges. Okay, it's a pretty useful tip. I think James talked about that in the last webinar. And again, we've got a couple of steps down in the bottom right-hand corner. So we've got a web thickness change and a pocket in the middle of one of these regions. Okay, so again, pick the surface, see the green line has appeared, bring cut line, do the same thing for the pockets, again selecting the contiguous edges, mouse button to accept, got that modification as we want it. Okay, just tidying up the surface with the vertex edge drag tools. If we had edges which were sort of free floating, then we'd see them within the meshing operation, but it's good practice to try and get your geometry as clean as possible before you get into the meshing situation. Okay, so there you go. There's the topology that we've built for this mid-surface. Pretty straightforward and pretty clean definition. Okay, I'm going to remove all the vertices. So just select the whole of the model. Again, keeping things nice and simple. Useful tips to bear in mind. Simple, avoids problems downstream, if you like. Okay, so we're now look into the mesh definition. Now that we've got the mid-surface defined, and we're going to look at a couple of tips here. Geometry is your friend. Okay, so we're going to use in this model, we've got a series of fastener holes around the periphery of the shear panel. So by defeaturing those physical holes, we can create hard points at the hole centers. Saves us a number of mouse clicks for mesh development. And then bear in mind that geometry modification, mesh update, and element quality display is all generative. So some of you may not be familiar with this, but basically means that if you change the geometry, then all of the model attributes, mesh properties, loading, and what have you will be updated accordingly. Okay. Tip 2, mesh itself can be used to highlight problems with geometry. So if you had a very small sliver surface in this geometry, you can use a rudimentary 2D mesh and then the grow 2D mesh, 2D 3D mesh to highlight any problems. And then we can use the mesh topology to show the edge status. So similarly here on the image that we've got top left, this is geometry where we've got red, green, and yellow lines. We can do the same thing for the resultant mesh to show the edge status as well. That can help us understand the underlying geometry. Okay. Tip 3, controlling the mesh. So we've got what we call feature mesh settings. so we can control the mesh at things like holes, fillets and chamfers, etc. So we can do that on a global basis and set different parameters for different dimensions. So that works nicely if you've got a complex model with lots of different size features in there. Bear in mind that you can use multiple meshing algorithms. So talking specifically about 2D shell meshing, we've got the auto, the pave and the map meshing algorithms. And that bear in mind, we can mesh single faces rather than the, well, over and above the whole surface by using the lower dimensional entity selection filters. Okay. So again, example here, just continuing. So again, this is the recording I made. So we've got to the point with the mid-surface quite clearly defined. So we're going to throw a mesh onto the structure. So before we do that, I'm just going to measure the distance between two features. So two typical holes. So pick an edge. The center is highlighted. So pick the center to an adjacent hole in its center. So we've got about 24 mil edge length. So we're going to use maybe 4 or 5 elements across that dimension. So we're going to end up with a mesh of about 5 millimeters that we're going to set to develop the mesh. Okay. So again, into the meshing tools. So surface mesh, set the mesh size, 5 mil. We're using the mixed, so the quad and the tri with the auto algorithm, leaving everything default. And we've got the mesh defined. Okay, so we can now start to look at some of the details and understand if there's anything that we can clean up or improve on. Okay, so looking at the element quality index, we can see we've got green, good elements and some poor and some bad elements, but we've actually got one invalid element. So this would mean that element is so badly distorted it won't run in an Apex or subsequent Nastran or similar type analysis. So we can click on the red element or the invalid element in the model, in the quality index fringe, and that shows the geometry with the failed elements underneath it. Okay, we can use what we call the Grow 2D 3D Mesh tool. So this grows the mesh around the failed element. Okay, and then we can start to dig into the geometry and understand any particular problems that we've got. So it'd been very difficult to find this edge if we didn't have mesh in the model. So if we put the vertices on, we can see we've got this this cut. We're just going to drag the vertex back to center. All the elements disappear because there are no longer any invalid elements, and then we can turn the display back on. Okay, so we've got about 6,900 good quality and then a handful of poor and bad, but the key thing here is that we've got no invalid elements halting what we're trying to do. Okay, so really quick way of tidying things up. You can see we've got a number of poor and bad elements around some of the hole features. So we've got pretty tight hole dimension given our 5 mil element edge length. So we're now going to use some of the defeaturing tools, I believe, to try and get rid of the holes and replace them with hard points. Okay, so we can defeature manually, but in Apex we've got this defeature by identified feature. So click the geometric entity, and we can do this for many entities in one hit, and then it will give us a map, if you like, of all the types of entities that it's found, or all the types of features it's found, I should say. And you can see here it's found lots of blue small holes, and if you look closely, it's found a green larger hole as well. Okay, so we don't want to defeature everything. We just want to remove the smaller blue holes. Okay, we can play games with the dimension range at this point. So if we had, I don't know, maybe 6 mil diameter holes and 5 mil diameter holes, we could get rid of just the 5 mils if necessary. Okay, so we just simply select the region in the defeature tree, and then middle mouse button, and then all those features are removed. Okay, just need to undo that step. We forgot to check on the create seed point in defeatured hole. So this will create a geometric point which shows up in the model browser, and then pulls out the mesh that we want. And each fastener hole, or rather each fastener point, is now hit with a shell element node. Okay, so really tidied up the mesh quite nicely. Okay. So once we've done our defeaturing, we can start to look at some of the discrete meshing techniques in it as a means to try and tidy things up. So with the element quality check turned back on, we've got a very small number of poor elements. We've got 25 poor and 2 bad out of nearly 7,000 elements. Okay, so perhaps not the most coarse, not the most fine model in the world, but again, it's a very good job in terms of picking those regions out. Okay, but you can see that we've got quite a bit of mixed quad and tri definition. So I'm just going to change the color of the points just to make them perhaps a bit more visible. Okay, and you can see here that this is a 4-sided shape. We've got all the nodes that have been hit, but we perhaps want to tidy up the mesh to remove as many of the tries as possible. So we can change the meshing algorithm to do just that. Okay, so go back into surface mesh, and now we're going to just change some of the features. We're going to mesh just the face of interest, and we're going to change the meshing algorithm from mixed to quad only. So yeah, by default, we've used the mixed mesh with the auto algorithm, but we're now going to switch to the quad only mesh and then the map meshing algorithm. So pick that face, so it's remeshed, and it's given us near perfect quads everywhere, and then just snap the node to the local fastener to give us the definition that we want. Okay, so we've just remeshed a couple of portions of the stiffener. We'll remesh this edge surface or this edge face. You saw there the map mesher wasn't perhaps the best tool, so we'll stick with the mixed algorithm. And again here, because we've got a fillet corner on the left hand side, the mixed algorithm is probably the best to use. If we've got these nice square faces, we can just quickly remove the tries as needs be. We could add some more splits into the geometry to improve things if necessary. Okay, but we're just removing as much irregular mesh definition as we want. And again, because this is all generative, just by meshing that portion of the surface, all the nodal connectivity, if there were properties on these shells, they'd all be tidied up as well. So lots of time saving here. Just looking at this stiffener edge where we've got this, or stiffener end rather, where we've got this tapered geometry. So we've put a split into the geometry. You can see the mesh updates automatically as we introduce those splits. So we don't need to delete the mesh, recreate the geometry, and then remesh. This is all handled in one hit. Looking at the algorithms here, I just play around with a couple of options. Again, it looks like the quad only works best on the flat faces, and then the mixed on the stiffener end. Okay, so just ringing through a couple of options here. Probably didn't quite get the right strategy in the first hit, but you can see it's very easy to make those changes as needs be. Okay, so we'll just move on to some of the other regions, and then we can see the effect of the meshing as we're working. Okay, so the tips we're using here is really saying that we can use the feature mesh settings and the defeaturing options and the different mesh algorithms to try and give us the best mesh that we can. So again, 7,000 good elements, 38 poor, 4 bad. Okay, and you can see here where some of those bad elements are. So we could spend a bit of time tidying this up. It runs through very quickly to give us the definition that we want. Okay. We've got this mesh flow optimization that gives us this nice distribution all the way along the stiffeners by keeping regular quads and then transitioning through tries as and when we need. Okay. So now we've got the mesh developed, we can start to look at attribution and verification. So a couple of things here. One aspect of mesh development or shell meshing is that you need to consider your surface normals and your XY directions for the shell. So every shell element has a local coordinate frame X and Y sits in the plane of the shell, and then Z points normal to that XY plane, if you like. So it's good practice to ensure that you've got normal consistency, and then you can think about direction. We've got something called the dual color display option, which we'll see. And then it's again useful to think about how you control the X direction that the shell elements are pointing in. So you want to try and get those things set before you move on to things like property definition. Okay. You can automate and visualize your properties. So we've got a pretty nice automation tool where we can build shell thickness and offset information from an underlying 3D solid. It's good practice to use the force constant thickness when auto-generating shell properties. What you probably don't want to have in this kind of model is to have different shell thicknesses where you've got discrete fillet features. Okay, and then once we've got that, you can use the section view tool to do all sorts of things, display and edit those properties that have been created. Okay. If you're going to be exporting your model, then it's probably a good idea to control your node element coordinate frame and material IDs to avoid external clashes, I should say. So if you're building a portion of a structure that's going to go into a master model definition, you may well have an ID range which your entities need to sit in. So you can control and modify those within Apex pretty easily. And then this is, if I was going to say anything, this is probably the most important tip of all the stuff we're going to look at, what we've been looking at today. So use the analysis readiness tool to understand if you've got any pre-analysis issues. And then irrespective of whether you're going to be solving in Apex or exporting the model externally, I would suggest it's good practice to always use, or rather always simulate, normal mode response for both parts and assemblies using the Apex Structures solver, just to make sure the model deforms and stress distribution develop or strain energy develop in a way that is expected for the type of structure you're looking at. Okay, so you can run through a quick, continue the demo on how you would do this kind of thing. Okay, so we've got the shell mesh fully defined. We're happy with the quality. We've got all the elements tied together. So if I can remember what we do next, we're just going to show. Yeah, again, we've got the transparency. Yeah, so we can show the mesh with the underlying solid in there. Okay, we've idealized the mid-surface in some of these thickness regions where we've got step geometries. But yeah, you can see the type of thing that's defined in there. Okay, we've got these mesh topology tools. So similar to how you would display the geometric line edges, so the red, yellow and green edges, depending whether it's a T-section, a free edge or a shared edge, we can do the same with mesh. Okay, so we've hidden the underlying surface geometry and we're showing the edges of the mesh and comparing that with the geometry. So good practice to do this before you consider the next steps. Okay, we can show that with and without the mesh, so we can put it transparent render to make the edge viewing more straightforward. Okay, so we can see all those nice connections in there, underpinned by the mid-surfacing, of course, but flown through to the underlying mesh that we create. Okay, so we're now going to start thinking about some of those attributions. So the first thing we're going to look at is the shell normal. Okay, so for every shell element, you have a top and bottom face. This shell normal dual color is pretty handy because it shows you the top and bottom without lots of hedgehog type vectors, if you like, on the screen. I don't know if you can see the vectors here with the white background, but the pink color is the bottom face and the blue color is the top face. Okay, it doesn't really matter which way around they are as long as they're consistent. Okay, so you can see with these stiffeners, so we're looking at the vertical stiffeners, this vertical stiffener in the bottom right hand corner is inconsistent with the other ones. It's pointing in a different direction. So we're going to just look at the element orientation tool, pick the middle option, and this allows us to pick an element, and then for all the elements connected to that face, they'll then be flipped over. Okay. Looking at the horizontal stiffener definitions, so we've got all these stiffeners along this bottom row. We're going to flip, so we've now got our normal consistency. Okay, so it's pretty important that you do this before you do your property definition, because if you do have shell offsets, if you flip your normals, it will flip the it will flip without flipping the offset, so that can get you into problems. If we look at the what we call the hedgehog plot now, you can see the vectors are all pointing consistent direction. Okay, for the large shear web, the upper flange, the horizontal and vertical stiffeners. Okay, we're now going to reverse the whole thing because we might want them all to be pointing inwards again. So we just do that in one hit. Okay, so perhaps a bit of overkill here, but just illustrating how we can control discrete faces and the underlying normal definition as well. We can look at the shell element XY plane. Okay, so one thing to bear in mind in Apex, every time you see a coordinate frame, it colors this with 3 unique colors, red, green, and blue. Okay, and the bottom left-hand corner, the global axis is always shown in red, green, and blue. So if you're always, so if you're unsure which is which, if you look at the global axis, it'll give you the XYZ annotation. So obviously, if this model had XYZ written all over it as well, then you wouldn't see a lot. But what we can do is we can align the X direction with a vector, or in fact, we can do that with an edge. Okay, so if you think we've controlled the shell normal direction, which is the element Z direction, we're now controlling the X direction as well. Okay, so if we zoom in after picking that vector, we can see all those vectors now pointing, or those local X axes are pointing in a consistent direction. Okay, we've got a second option here. We can use curves, so we can pick all the elements or a subset of elements that we might want, and then pick all of the edges all the way around the surface geometry, select contiguous curve, and then that gives us the X direction that follows the edge all the way around as best it can. Okay, this can be quite useful if you're looking at element output, shell forces and moments, or stress components, and you want to control which is the X or Y direction without having to do transformations in a post-processor. Okay, but again, we've got lots of control here, picking discrete elements to focus whether we want a vector or an edge. Okay, so once we're happy with that, we turn off the elements coordinate display. We can start to look at the shell property definition. So we'll put the solid back into view. We're going to develop the shell properties from those solids. Okay. And so we're going to force a constant thickness, so we don't get steps where we've got the local fillet section changes. That could give us a very messy model. Okay. If you did want to look at fillet section changes, you'd probably want to be looking at a 3D model. So by forcing the constant thickness, it does simplify things quite nicely. Okay. So pick the face, pick the solid, and generate those properties. Okay. Seeing there very nicely how they're generated. Turning the shell thickness on, and with the 3D solid in transparent mode, you can see how well it's done mapping those shell properties across. Okay, just want to show you the section view tool now, just to make clear sense of all these definitions. Okay, so some of you may be aware of this. This is something that I stumbled across, and it does make things a lot easier when you're mapping shell properties. So in the model browser, if you switch view to section view, this gives us a color-coded mapping of all the thicknesses that have been calculated from the underlying geometry. Okay, now this geometry has quite a lot of detail in it. So what we can do is try and map consistent shell property sets across common regions. Okay, so we're just picking these vertical stiffener faces and the mouse button to accept, and you can see the colors are now matched up. Okay, so we can work our way around the model and develop exactly what we need. Okay, so yeah, just repeating that now for this top flange. Okay, so can just pick those regions, set to a common property set. Okay. You may see in the model browser we might have a particular property where the offset has been calculated at a very, very small value. So the mid-surface for that region wasn't quite aligned with the CAD based on maybe some taper to the CAD geometry or something like that. So what we can do is we can double click on that feature or that property set, and we can change the numerical values as we see fit. Okay, just repeating this step a second. So double click on the property, click on the sign, click on the section, and then yeah, we can click on the offsets on the right hand side, and then the value is corrected in the model browser tree. Okay. Typically what we do now is start to look at the IDs for the model and then check the model run response, but I'm going to skip those steps in terms of the time that we've got left on the webinar. Okay, so one final part of the workflow, looking at orphan model manipulation, and this is where you've got legacy BDF definition or legacy FEA model. So tip one, old is the new, as it were. So you might have a legacy certification BDF. So typically speaking, Nastran or external FEA data isn't always stored with CAD geometry. So if you've got the FEA model, don't worry. You can build and manipulate as you see fit. Okay. You can generate the appropriate geometry form. So we've got two types of mesh. Excuse me, CAD that can be derived from mesh. We can create faceted bodies, which follow the mesh form, and we can create NURBS smooth geometry if we want to look at higher fidelity meshing. Okay, controlling the legacy model. So you need to set the appropriate unit and assembly options when you import a model, and then we can look at local remeshing of that geometry or those facet bodies, and it will retain the legacy mesh away from the region of interest. And something useful to bear in mind is that the shell properties are remembered through the manipulation. Okay, tip number 4, you're good to go. Any geometry generated from legacy mesh can be exported to CAD. Okay, so just running through the last demonstration example that we've got. So again, bringing in a model now. So no geometry, just cycling through to the bulk data format definition, bringing in the BDF file. So we set the model units, so millimeters, millimeter model in this case. The entities come in, and we can see we've got the mesh definition in there. We've got the shell properties defined, and we can start to play games with this. So let's say we wanted to manipulate the structure, maybe add some feature detail. We can see we've got all the shell sections in the model browser, and the materials have come in as well. So we're going to create a facet body surface from the underlying mesh. Okay, so in the geometry edit tools, we can do that quite easily. Avoid the need to be rebuilding geometry. Okay, so we're just going to bring in a new rib, if you like. So this new rib has got very similar topology, but we've got some lightning holes in it. Okay, so we could in fact build this whole geometry from the mesh. but just going to show you some editing of what we can do in this particular type of workflow. So we've got these lightning holes, and we want to introduce those into the underlying mesh. Okay. So we go into the geometry edit tools, and we can create, where are we? Bottom left hand corner, geometry from mesh. Take the defaults, pick the mesh, and it creates a series of geometric entities, and we can edit these if necessary, but we can just then select the body as we want, hit the green tick button, and if you look on the top left hand corner of the model browser, we've now got a faceted general body. Okay, and this can be used for model manipulation. Okay, I'm just going to skip on a little bit here, just to just for a time purpose, but you can see here we've actually manipulated those faces from the underlying geometry, and the shell properties have been retained, so we haven't had to revisit the whole of the mid-surfacing and meshing operation. The shell properties have been retained, and we're pretty much good to go. Okay. So, in summary, some of the best practice stuff that we've got from geometry preparation. Keep things simple. So, talked about cleaning geometry before you start. Don't defeature where you don't have to, and then delete unnecessary edges and vertices. Automate when you can. So use tools like extend and stitch where possible to speed up your workflow. Use the appropriate mid-surfacing tool to suit your geometry complexity. And then thirdly, tip 3, be clever with your display options. So use auto color within the model browser, and use transparency to compare your 3D geometry with your underlying mid-surface and shell mesh definition. Okay. From a mesh definition perspective, geometry is your friend. So you can defeature your geometry and create things like hard points that fasten holes that the mesh will be forced to follow. Mesh can be used to highlight problems with the geometry. So if you remember, we looked at a mid-surface where the we had a cut edge that wasn't visible, but only became apparent when we looked at the mesh quality. And then we can control the mesh with things like feature mesh settings, using the appropriate algorithm, and meshing with low dimensional faces. Attribution and verification, orient your elements, both in terms of shell normals and shell XY direction. Automate and visualize your properties. So use the section mode to look at your property sets and how they're distributed in the model. And then finally, check that your model runs. This is probably the biggest tip of all, I would say, using the Apex Structures license. And then finally, looking at orphan model manipulation, you can use the tools to create the appropriate geometry from a legacy PDF file. And you're good to go in the sense that any geometry that you create, you can then export to an external CAD system. Okay. So that's the conclusion of the slide presentation, the demonstration I wanted to run through today. Run over a little bit, but we've still got probably about 10 minutes left for questions and the like. Are you on the call, James?
Yes, I am. All right. So we've had a very lively Q&A over here, and we're probably not going to be able to get to them all. So I apologize ahead of time. But some of the really cool ones that came out, I'll read them to you, and you can answer for me. So the first one is, let's say you have a solid piece of geometry. Can you actually draw on that solid body and create geometry, not just import CAD?
Absolutely. Yeah. So Apex has a full suite of sketching tools. And it also has things like push-pull, some of the direct modeling functionality, which you can use to create 1D, 2D, or 3D geometry, either freestanding or connected to your CAD model that's come in.
Awesome. Thank you, Steph. We've had a number of different questions asking about automatic parameter updates, whether it's thickness, whether it's mesh, whether it's all sorts of things. So I'm going to kind of combine some stuff, but the question itself is, when the geometry or the location of the mid-surface changes, walk us through a little bit about how Apex automatically updates that.
Okay, well, I'm not going to run through that live on Apex, as it were, but if you were to change your mid-surface position, or the position of the geometry, or indeed a section change, then you can either use the auto thickness tool to repopulate your shell properties, or you can manually go into the section view tool and change thicknesses and offsets in there. But both of those are generative in the sense that they will wash through the model and you know, any mesh that's already on there. Okay.
Perfect. Thank you, Steph. And that was a good lead in to, I'll throw a comment in here too, which is, no matter where in the world you are currently located, if that question kind of sparked your interest and you have more interest in seeing it live, please reach out to us, mscsoftware.com, or any of your local application engineers or your account manager, and ask for a demo of this, because there are Apex specialists in pretty much every country around the world. And if there isn't, we'll get one close to you, and we'll have a nice long 2 or 3 hour discussion, and we can go as deep as you want with mid-surfacing and shell meshing and automatic updates. That's a question that's really kind of difficult to answer in a quick 5-minute question. All right, so the last one that we'll do, and then we'll cut it off for today, which is during your demo, you did a certain amount of mesh customization. Can you parameterize those mesh settings?
Absolutely, James. Yeah. So we've got the feature mesh settings. So if we wanted to maybe repeat a ring of elements around a fastener hole, or around a 2D fillet or chamfer or something like that, we can control those types of things. And equally, they're all applicable to 3D meshing as well. So you don't need to be spending long time manually mesh controlling these things through the use of the feature mesh settings.
Perfect. Awesome. So I'm seeing we're still getting more and more questions. So please don't hesitate. We're out of time today, but please don't hesitate to email us or contact us. Steph.evans@evotechcae.com or james.pura@mscsoftware.com. Or basically anybody that has an MSC or Hexagon email address. Just email us, and we'll somehow get your question answered as quickly as possible. All right, and we can do some demos and all sorts of good stuff. Thank you, everybody, for attending today. You will be getting an email with the recording afterwards, so that you can feel free to send that on to your colleagues. And also feel free to send, if you like this and you think that some of your coworkers want to see it as well, please forward the invite to them, and we'd be happy to see them on a following monthly webinar. Okay, thank you very much.
Thank you. Goodbye.